What's up guys? Programming with Mati is finally back. It's been a while, but during all this time I've been really busy with work, but also I was able to learn a lot about different topics like functional programming, which has become sort of a passion for me. And I've been learning a lot about this and I wanted to share all this with you. So I'm going to be preparing a lot of content for this part of the year about functional programming. And what is functional programming? It's a programming paradigm that has been around for quite a while now, but it's been recent since the major programming languages have been adopting this programming style, and Java has not been the exception. Since Java 8, we have seen a lot of features of functional programming being adopted in this language. So I want to share with you all this so that you can take advantage of this functionality and improve your programming with a lot of new cool features. So welcome to a new episode of Programming with Mati. Alright, so let's start from the beginning. What is functional programming? I would say it's a programming paradigm that views computer programs as the application of composed functions. So basically, we compose functions and we apply those functions to data so that we get an outcome. As Java developers, we're not used to think about computer programs as the execution of composed functions. We rather think of programs as the execution of steps, orders, or statements. And the building blocks of a functional programming language are types, which is basically what types of values can we hold as data in our program. Then we have the values, which are the minimal expression, cannot be reduced anymore. It's just a value. And then we have expressions, which is basically combining values with operations. And finally, we have functions, which is basically naming a set of expressions so that we can reuse them. The features of a functional programming languages are that functions are first-class citizens. This means that functions are objects that can be sent as parameters, returned as output. They are objects in the language, and they can be used for everything. They can be interacted with, they can be composed, they can be operated. Another characteristic of these languages is that data is usually kept immutable. And that means that when data is set to a variable, then that variable cannot be changed. And the reason for that is that we want to keep referential transparency, which is just a fancy phrase for knowing the value of a variable always. When you set a variable and you cannot change its value, that means that you will always know what that variable holds. And that also helps you reduce unexpected behaviors. And the last thing that these languages tend to favor is the usage of pure functions. A pure function is basically a mathematical function. This means for the same input, we always get the same output. And if you ask a mathematician what a pure function is, he will probably tell you, I don't know. There are functions and there are things that are not functions, but there is no such thing as pure functions. And that is because pure functions is mostly a computer science concept and not a mathematical concept. Because we probably have been calling function things that are not functions. For example, if we have a function that writes into a log, for the same input, this function will return different values. Or actually, some of these functions don't return anything at all. But we know that the function did something. And it didn't do the same thing if we call it again. For example, if we write into a log and we call the write method with hello world once, we will write into the log hello world once. If we call it twice, then we will write into the log twice hello world. So basically we're modifying the state of the log file. So what are the advantages of functional programming? And the main advantage I find here is that it's a declarative language. So instead of telling the computer how we're going to do something, we try to tell the computer what are we going to do. We don't have to worry about control structures like for loops, if statements, switch statements. We have different tools in these kind of languages, which are smart data structures. We have expressions more. We favor expressions more than statements, and that makes our code more declarative, which makes it simpler to write. It's easier to read and to reason about it, and it's also very easy to test. And this is a great advantage. If you love TDD like I do, then you probably love functional programming, because testing functions, mathematical functions, is very easy. Because it's always for the same input, you always have the same output. So it's really easy to prepare scenarios for these kind of functions. How does Java support functional programming? Well, since Java 8, Java has added some support for functional programming style, mainly the functional interfaces, which in turn allow us to create lambda expressions and method references. And if you don't know what lambda expressions and method references are, I'll encourage you to take a look at my video about this very same topic, where I explain extensively all the different kinds of lambda expressions and method reference and how you can use them. So check out the video. And finally, we have higher order functions in Java implemented with data structures like stream and optional. And when I say higher order functions, what I mean is they are functions that can receive functions as parameters. That's why they are called higher order functions. For example, the method in stream, we have a method called map, and that map method transforms the stream into a stream of a different object. So we effectively map each object of the stream into another object. That's a higher order function, because it receives a function as a parameter. So is then Java a functional programming language? Not quite. Java doesn't have a good support for recursion, which is a very well-known feature of functional programming languages. It's also very hard to have immutable data in Java. For example, if you have objects that have objects as fields and they also have objects as fields, it can be very tricky to guarantee that you cannot change those objects. If you have an object that has a list as a field, it's harder to guarantee that someone won't add elements to that list, and that would break the immutability principle. So this is quite tricky in Java. It's not that it cannot be done, and there are libraries that help with this. Also, some of the more advanced functional patterns are really good to be used, but because of the language limitations, when you write them in Java, they are quite hard to read. So the language doesn't support them very well yet. And there are libraries that help to make Java even more functional. And they have their own implementations of the collections, libraries, and functions and functional patterns. BABR is one of them. It's really good. I haven't been using it a lot yet, but I have been reading their documentation, and I can say that it's really, really good. And I'm looking forward to try a little bit more. So I want to introduce functional programming with a tutorial, as I always do. And this tutorial is called Paths. And basically we have a Google Maps kind of API that returns a list of paths from point A to point X, right? So each path has a list of segments, and each segment is composed by 2 points, and each point has 2 values, the X value and the Y value. It's a very basic implementation. It's just for the sake of understanding functional programming. This is not extensive implementation of any kind of GPS API. And then what we want to do is we want to develop a function that returns the shortest path in the list. And then also we want to create a function that returns the shortest path in the list, but it also has to contain some particular points. So let's get right into the code. All right, so before we jump into the code, I wanted to take a time to thank you all for your support and all your comments. And as always, the code for this tutorial is going to be in my GitHub repository. And if you want to follow along from the beginning, you can do it. But if you think that the first part is a little basic for you, you can feel free to move to the middle part of the tutorial where we are going to go deeper into functional programming concepts. So let's go and let's start coding. So I'm going to create my new project in IntelliJ, and it's going to be named FP for functional programming. Let's say Path, Java, Kata. And let's say, yeah, Maven project. And we're going to put the package name com GitHub programming with Mati. Okay, so we have our project here, and the first thing that we're going to do is create our class, which is going to be the point class. So let's say point, and it's going to be a record, which is a new feature in Java. So let's try it out. And this record, with this point, we said it's going to have a 2 points. So 2 values, the x value, and I'm going to use big decimal. So we have 2 values in each point. We have x and y. Fine, and we're going to use big decimal because we want to keep things interesting with some methods in big decimal, and also to because we are going to be using calculations and we want to keep the calculations as accurate as we can. So yeah, let's use big decimal. And now we're going to create a test class for our point class. So point, yeah, we have a test class, and it's breaking because we don't have JUnit. So I'm going to add JUnit to our project. Now let's wait a few seconds, and yeah, let's create our first test. And the first test is going to calculate the distance between 2 points. So I'm going to say void test distance. Okay, and for these I'm going to create 2 points. So new point, let's say big decimal 1 and big decimal 0. Okay, and I'm going to create another point, new point, big decimal, let's say 0, 0, big decimal 0. Okay, and let's put it into a variable. So let's say 0.2, and let's call the first one 0.1. So let's calculate the distance. So distance will be a method, and we're going to create it as a method. In a pure language, in a pure functional language, this wouldn't be a method. This would actually be a function, and it won't be inside the class. It would be, we could say it could be a static method. So it could be something like point dot distance, and we would pass point 1 and 0.2, let's say. Okay, but I really don't think we have to go that far. I mean, Java is a object-oriented language, and we can use its object-oriented features. There are some features that we tend to use less now, like inheritance, for example, which we try to avoid. But there are some very useful features in the object-oriented programming paradigm. So I will implement this as a method, and this method is going to call, yeah, another point. We need to send a parameter, but this method basically has two parameters. It's the same. We have the object in which it's going to be called, and we have the second object. So it's basically the same. The only thing that we need to make sure is that this method doesn't modify any data at all, and we'll be fine. So yeah, well, this is going to return a value, let's say distance, and then we are going to have an assertion, and what's going to be the distance here? So the distance is going to be actually we need to implement the function. So let's implement this function, and let's say this is going to return a big decimal, which is the distance, and we have other, and it's going to return null for now. And then we have here what we are expecting here is a value. So basically we have to implement the mathematical function for the distance between 2 points, which is x, so 0.1 x minus 0.2 x, and this will have to put to the power of 2, and the same we're going to do with y. So p1.y minus p2.y to the power of 2, and then we have to apply square root to all this. So we're going to say basically square root of all this. So this is what we need to calculate. Okay, so we will have to calculate this. Let's say this is going to be 1 plus 0 is 1, so it's going to be 1. At the power of 2 is still 1, and then 0 and 0 is 0, at the power is 0 still, so square root of 1, and square root of 1 is still 1. So I think we should be fine if we add here just big decimal 1, and we're going to say here distance. That's it. So let's see how this runs. Okay, we have our first failing test, so we can implement our function now. We could basically say return 1. That would be valid, but let's just implement it because we know what the function is. So it's basically this. Let's say we have this x subtract other x, and we want to this to the power of 2, and we want to add all this to this y subtract other dot y, all this to the power of 2, and we want to have the square root of all this, and math context decimal 64, that should be fine. Good. So we're basically doing the formula that we said just before, and now let's run the test again.
let's just write one test in which we validate that the point is not null, point that we're just sending here, when point 2 is null. Okay, so if we send this as null, we could basically say objects. So we want to validate, and because we don't want to fail, what we could say is that if we have null, we could imagine that we're receiving the null point. So basically it would be the 0 point. So we could say new point, big decimal 0, big decimal 0. And we are going to have other, and we're going to use this other for our calculations. I forgot to add other here, and here we go. Yeah. Now if we run our tests, brilliant. And the other thing that we could validate is that our initial values are not null. So let's run one more test. Let's say when initial values are null. And we can take the same approach. If we have null, we can assume it's a 0. So let's see. Yeah, let's just, for the sake of our test, let's just assume it's a 0. But we could eventually say that no, actually, if we are receiving a null, then we want to alert someone, because they might not be sending null on purpose, and it might be good for us to, instead of doing this, sending them a warning or an exception saying you're sending null here. But for the sake of this test, let's just assume they are trying to send 0 when they send null. And so if we send a new point here and say null, null, we could assert 0 0.1 x 0.1 y. Okay, so now how do we do this? I think we have to say public point x objects require null else x, then big decimal 0, and the same with y. So why is this failing? X cannot be assigned. But this is the constructor, right? Say, put it like this. Yeah, now it's working. So let's try our last test. And it's working. So everything is working. Okay, so now that we have our point class, let's go on and create our segment class. And the segment class will be, so segment, and will be a record as well. And we said we're going to add, oh, actually, it seems like I'm using the wrong package. So I'll go on and create a package here. Come GitHub programming with Mati paths. And let's go and move this here. And I think I will have to add a new package also in the test folder. So new package here, and let's put this here, and we're good to go. Brilliant. So now segments. So segments should have 2 points. So they will have point 1, point 2. Okay, so now let's create our test class. Oops, there we go. And now that we have our test class, let's go on and create our first test distance. Okay. So we will be able to calculate segment distance. So a segment will have 2 points. So let's go to our point test here, and let's just get this. Not this one. This first one. Yeah. Here, and let's just copy these 2 points that we have here. Yeah. And let's use them to create our new scenario. Yep. So this will be point 2. And we are going to create a new segment. Point 1, point 2. Let's put it into a variable. So segment will have a method segment dot distance, and it doesn't receive any parameters because the segment has the 2 points, so it's an implicit parameter, which is a segment. And let's put it here and say distance, and we know the distance for this is basically the same distance between the points, which was 1, so big decimal 1, and distance. Okay. And now let's create this method. This is going to return big decimal, and we're basically our implementation will be point 1 distance point 2. That's it. We could create a new test for validating that the points are not null. So how do we do that? Okay, we could. All right, so let's create our constructor here. In this case, we'll return an exception if some of these are not there. So this point 1 objects require not null point 1, and the same with point 2. And if these fail, if this is actually null, it's going to throw an exception. So let's go. Oh, actually, I didn't create any test for this, so my bad. Sorry, guys. I need to create a test for the case test constructor when points are null. So let's just grab one valid point, and let's say new insert rows, no pointer exception, and this is in here. We have to send, so we say what kind of exception we're expecting, and then we also say what is it that we expect the exception to be thrown in. So the statement that will produce the exception, in this case, is the constructor. So segment, and we're going to send 0.1 as a valid and then null. So we're expecting this to throw an exception, and we're also going to test the other way around. So null here, 0.1 here, and test. So let's run this. Yeah, everything passes. So that's great. Do we need anything else for now in this other than the distance? I don't think so. We got, yeah, distance, and we are validating that the points are there. So seems good to me. So after that, we have to create a new class for the path. So let's go with path, and it's going to be a record. And path will have a list of segments. And this is going to be a list of segments. Let's call it segments. And we are going to also have a method for the distance. Public distance, public big decimal distance. And we don't know still what the implementation will look like, so let's go on and create a test for this class. So I don't know if you see how I create tests here, but I basically do option enter here, and we have an option to create a test. So it will create a test in a similar package, but in the test folder, which is quite handy. So I create a test, and I do test void test distance. Okay. So now we need to create a path with at least one segment. And actually, we can start with maybe a path that doesn't have any segments. What do you think? So yeah, we can start with that. Let's say bar, not bar, new path, and collections empty list. So we're going to send an empty list. We have our path here, and we're going to say let's set equals big decimal 0, because the distance should be 0 for a path that doesn't have any segments. And that's it. So strictly we could say big decimal 0 and run our test. Good, it works. All good, let's go. No, just kidding. Let's just rename this to one no segments, and let's have create a new path. But now test distance one segment, and we can actually use our segment from the segment test, right? So we can say okay, here, and we put the segment here. This off and segment. So it's a list of one single element. And now if we run distance, we should get the distance of this one segment, which I think is 1. So let's do this. Actually, we could say if it is empty, just return 0, else get the first one and return distance. But I mean, then we'll have to create a new test for more than one element, which I guess is redundant. So let's just go ahead and implement the logic. And what we need to do here is basically we need to go through all the segments and add up all the distances. So actually, let's go back a minute. If you notice, everything that we have implemented until now are pure functions, because these functions don't modify the values. They are only depending on the parameters. So the parameter is the implicit parameter in object-oriented design, which is the this element, but it's still a parameter, and we are not modifying it. We're not doing anything else. We're just using the parameter, and depending on the parameter, we obtain a value. So if we would send two different set of points here in the point set, and we call the method distance, we would get a different result. And for the same set of points, we will get always the same result, no matter what we do. Every time we call distance for the same 2 points, it's going to be the same. We could actually memorize this function, and the word is here is memoized. This means you can basically store the return value in a memory, and you can pick for the same 2 inputs, you can pick this value that we have stored, and we can just return it instead of calculating again, because it's always going to be the same. That is a good way to figure out if you're doing a function, if your function is actually a pure function. If your function can be memoized, then it means it's a pure function. So now in our path class, we're coming up with a more complex algorithm. In an imperative language, we would create a for loop, and we would say for each segment in segments, and we could store a value, let's say var distance big decimal 0, and then we would go on and say distance dot seg distance add, and we would say distance add segment dot distance, and then return distance. That is right? So we are looping and then returning, and this would be the way to do it in an object-oriented programming language that doesn't have functional programming features. But since we do have, we could use a more expressive way to do this, which is, for example, using the stream data structure. We could say return, and we can get the list of segments, and we can map this list of segments to the big decimal value, which is the distance, by saying, for example, segment and segment dot distance. And then once we map it to the distance, we can reduce it by using a binary operation. And because we have big decimals, what we can do is big decimal add. And in here, I'm going to apply something that we used in our tutorial about lambda expressions and method reference. I'm going to replace this with method reference, because this syntax seems a bit redundant. It's segment distance. So Java knows how to simplify this by saying call the method distance in segment, and that's it. It is a method reference. So I encourage you to look at my method reference tutorial, where I explain everything about method references, how you can use them, all the different types of method references, and lambda expressions. Okay, and I'm going to do the same here. So look at this. Look how expressive this is. this is so for each segment we are going to get the distance and then add all the distances. And because this could be empty, so segments could be empty, we need to return a value in case that is empty. So you see this is going to return an optional. What we're going to do here is going to say or else big decimal 0. So basically, if there was no elements to reduce, we're going to return 0, which is exactly what we want, because a distance of an empty path is 0. And look how expressive this is. So we have the list of segments, we take the distance, and we reduce all the distances by adding them together into a single value, which is basically the sum of everything. And finally, we return it. And if there was no value, we're going to return 0. So let's see if our tests now work. Let's go to path test. And let's run all the tests. The one with 0 has to still work, and the new one, well, it has to work. Good. Yeah, it works. That's great. So how do you like it best? I really like this expressive way of working. I don't have any loops here, any structure. Yes, I have some new functions that I need to learn, but it's not that bad. And I think it's more expressive, and it really tells you what's going on here. You don't have to figure out what is this variable and what is this doing, and it's straightforward. So yeah, that's great. So we could probably add one more test in our path test for 2 segments. What do you say? Say just if it works for 1 and it works for 2, then it works for every, right? Okay, so 1. This is the first segment, and let's just copy this, create a new pair of points, 3 and 4, segment 2, segment 1, just say segment 1, segment 2, and the second pair of points is going to be, let's say, big decimal add big decimal 1. This is going to be 10. Okay. So if we do this, now what we can expect here is to have segment 1 distance add segment 2 distance. So the path distance is going to be the same as the addition of the other two the 2 segments. I forgot to add this too. Okay. So now let's run our test and let's see, it should pass. Yeah. Good. We're doing a great progress. So going back, if we see one of the concepts that we are using here of functional programming is basically what we call higher order functions. So map, reduce, these 2 functions are actually higher order functions because they receive as parameter a function. And this is what we speak about when we say that functions are first-class citizens. We can send functions as parameters, we can send functions and we can compose them together like this using this string data structure. So this is something that we could do with Java before, but it was really hard because lambda expressions made it really easy to work with functions and higher order functions. With the lambda expression and the method reference. And you can see that this distance is always going to return the same value for the same set of segments. This will never change because segments don't change, points don't change. So if you don't change anything, if you call distance to path, to the same path, it will always return the same. There's no way you can change the path, because this variable is a final variable. So if we respect that, if we don't change the path, then this distance will be always the same, and this is by definition a pure function. It's tricky because we're working on an object-oriented language, and because of that, it doesn't look like we're sending a parameter, but the actual parameter is the object that receives the call. So the this object is the parameter. So as you can see, functional programming has been very useful for us, and it's been really easy to test. So I feel like this kind of programming is very helpful for us to work with unit testing. So what do you feel? Just let me know in the comments. What are your feelings about this? How do you see this working? Do you see that this is going to be useful for you? I would really love to hear that. But let's go on with our tutorial. We have to create one more class, which is going to represent the list of paths. So we'll have a list of paths. We'll call it PathList. And it's going to have a list of paths. So what we want to know about the list of paths is, first, we would like to know what's the shortest path. So let's create a test for this. And our test is going to say test void test shortest path. And we will have, so let's go on and create, let's create one with a when no paths. Okay, so if we don't have paths, what is going to be the shortest path? There's none, right? So usually what we would do, what would we do in Java? We had a few options. We could either throw an exception, or we could return null. And I don't like any of those. So let's say we have a new path list which receives a collections empty list, and we do assert null path list and this shortest path. And it's going to return a path. But we are going to return null because it's empty. So what's the problem with returning null? The main problem with this is that if I do something like this, this will throw an exception. This will throw a null pointer exception. Why? Because distance is a method being called on a null reference. You see here it's asking me to assert that this is not null, and I don't want to do that, and I don't want to throw an exception either. What I'm going to do is I'm going to make use of a new data structure in Java 8, which is called optional. And this is also a concept that comes from functional programming. So I'm going to return an optional path because I could return a path or I could return nothing. So basically I could say optional empty. And here, instead of assert nulls, I'm going to say assert true. And here I'm going to say is empty. So what I'm testing here is that we don't have any paths. You see? So there's no risk of exception here because this is always going to return something. And there is a concept in functional programming called totality. And what it means is, for a mathematical function, you need to define an output for every input. So every input that I can send in has to have a output. And that means that the function is actually a function because it has every input mapped. I cannot have inputs that are not mapped to anything. So how do I handle a path list that is empty? I need to return something. If I don't return something, if I say that this returns a path, but there are some cases in which this throws exception, then the signature of my method, it's a lie. If I say that this returns path, but actually this could also throw an exception, or this could return null, this is lying. But if I say optional path, now I am defining an output for every possible scenario. If the paths is empty, then I will return an optional empty. But if the paths are actually we have a list of paths, then I can select the shortest one and return an optional off. And I could send a path here. And let's see how we can do that. Let's just create a new scenario. But this is an important concept in functional programming because it tries to define functions as pure as possible, and it also this gives you control. This gives control back to the user, to the client of the API, which is what we want. So let's go on and create shortest path, one path, let's say. Okay, and let's create one path. So we have the path test here. We have one path, and let's create a path with one segment. And let's put it here. Let's say list of, and we can say shortest path. And in this case, we're going to assert true is present. We're going to say assert equals, and we could say segment distance, and we could say, let's put this into a variable, actual path. We could say actual path dot get dot distance. Okay, so let's run this test. It's not working. Why? Oh yeah, we haven't changed the implementation yet. So let's go to shortest path, and since we have, let's say, only one path, we could say paths stream and we could say find first. So if you look at this method, find first, it returns an optional path. Why is it returning an optional? Because the list could be empty. So if the list is empty, the optional will be empty. But if the list is not empty, it will return an optional with an actual path inside. So if we run our test now, we will see that our test should pass now. Yeah, excellent. So we should probably add one more test for 2 paths. So we have path 1, and let's add a second path. We have 0.3 and 4, and this could be 1, this could be 10, and this could be 10. So segment 2 will obviously be larger than segment 1. 3 and 4, and we'll have path 2. This is going to be path 1, this is going to be segment 1, and this is going to only have segment 2, let's say, and then we say path 1, path 2 as a list of paths. So now shortest path is going to be path 1. So we could say path 1 distance and actual path should match. Let's mix them up so that we have to change our implementation. So if we run this now, it's going to fail because we're getting the first one, but the first one is not the shortest. So let's implement the shortest. How do we get the shortest? So stream has a very nice way to do this. It has a method called min, and min will return the minimum of a set. Let's remove this. And what it has to take as a parameter is a comparator. The comparator is basically an interface that is a function that compares 2 different values. The comparator interface has a lot of helper methods to create comparators very easily. So we can create a comparator for our field that we need to compare, which is the distance. So we can say path distance. So basically we could implement this. Let's implement it on a different way. So basically we could say comparator, we have 2 objects. Well, actually we could use the comparator method in big decimal, compare to 02, and that should be distance, sorry. That should be it. But now here's what I was talking about before. Comparator has a lot of different methods, helper methods, to create easier comparators. So it tells me to replace it with comparing with distance. So basically this is the same as this, but it's just clearer. So now we are returning an optional. And again, why are we returning an optional? Because we need to figure out if the stream was actually empty or not. That's why it's an optional. And as you can see, min is also a higher order function, which receives a parameter, which is a function, a comparator function. This returns a function, a comparator, which is basically a function for comparing 2 values. So this is a higher order function. And now we can run our test again. Let's see what happens. Ah, still fails. Oh, I see what the error is. So these points are actually the same. So this is actually the shortest path because the difference between these 2 points is 0. So that's why it's returning a path with 0 distance. Actually, let's change this. I mean, it's good, but it doesn't work for our scenario. So we want path 1 to be returned. So let's try that. Let's run it again. Let's see if it works. And it works. Brilliant. Okay. So now that we have the shortest path, so now if we look at our instructions, we need to create a function that returns the shortest path in the list that also has some particular points. So we need to send a list of points and we need to filter, we need to look for the paths that actually have those stops. So okay, so let's say, so we have this path here, right? And let's use this with point. Let's say 1 point is not present. So we have these 2 points, so let's create a third point. Let's say point 3, which is going to be 10, 0. So point 3 is not present in the segment, so it's not present in the path. So we send point 3 as a parameter here. We say shortest path, and we can create it. Let's create a new method for this. Like point, and because the point is not present, we should return path. We should return optional empty, right? And this is going to be is empty, and this should be there. I need to say here optional path. Okay, so the point is not present, and this will run because I basically hard-coded the empty there. But if we add a new test and we say that the point actually is present, so say point 2, so point 2 is there, so we can we need to figure out how to know if the point is there or not. So how can we do that? So I guess we could list all the points. How would we do this on imperative programming? We would say we have this point. This could be quite hard. I mean, we would need to go into and do many for loops to get this, I think, because we would need to go into the paths and then inside the segments and then inside the points and get all those points and compare against our point. But maybe with functional programming we can do this easier. So first we can take a look at this. Let's just copy it. So now we want the shortest path again, which is this function right here, but we also want the ones that contain this point. So how can we say that? So stream has a method which is very useful, called filter. And filter will basically filter all the elements of the stream that fulfill a particular predicate, a particular condition. So we could say the condition is that the path includes this point, right? So we could create this method. So let's create it. And this method right here, we need to, for this map, we can do, how do we know if it includes the point? We could say point, no, sorry, segments, string, and we could map, we need to get the list of points for each segment, but we want to keep it all in one stream and keep each point as a element of the stream. So we can basically say flat map. So we'll map every segment as a, and we will create a stream of the different points in each segment. So segment point 1, segment point 2. So now we have mapped every segment to its points. Yeah, so now we have all the points, so we can count the points, for example. Sorry. So now that we have all the points, we can filter them with a predicate saying that, for example, point P has to be equal to point, and then we could ask any match. So any match will basically say, have you find at least one? Oh, actually, any match takes a parameter, it takes a predicate here. So we could say predicate is equal to point, and we can add this as a static import so that it's easier to read. So you see, this has created a predicate which compares the values of the stream to this point. So any match, what we'll do is it will run the condition against all the elements of the stream until it finds one that matches, and that will return true. If none match, then it will return false. So I think we're good for our scenario now. We can run this, see what happens. All the tests should pass. Oh, it's not passing. Actually, this is not empty, it should be is present. And actual path, yeah, that should be it. So let's run it again. Okay, so this works for a single point, but we want to send more than one. So let's create a new test and say 1, 2 points are present. When 2 points are present. So we have 2 points that we're going to ask, and we know these 2 points are present, so point 2 and point 1. And we'll have to adjust this to receive multiple points. And the same here, it has to receive multiple points. So now that it receives multiple, we can, this doesn't work anymore. because we'll need to ask if all the points are contained. So we need to compare it one by one. But one thing that we could do is we could count all the points, right? Points count, and we can compare this point count to points dot length. So if they are equal, then it means all the points are contained here, right? Oh, but actually I need to filter first. I have to create a custom predicate. The point has to be contained in this list of points. So we could turn this into a list. So arrays plus best points. And this we could say contains point. So now if this is contained here, we will only keep those points that are contained in our point list. And then if they were contained, they will be counted, and then we will compare it to the count of our parameters, and they should match. So let's see if it works. And it does. But I think we are not covering all scenarios, but because what happens if a point is actually repeated in the path? And this is usually the case, because if we have two segments, let's say we have two segments, usually the first point in the segment would be the last point of the previous segment. Let's say this is going to be 0.3. Okay. So this is going to be our segment 2, this is segment 1, segment 2, and we have when 2 points and points are repeated. And this should fail. Yeah, it does. But there is a solution for this, and in our includes method, what we can do is keep only those points once. So all the points that match this are going to be kept once, and we're assuming we are not getting repeated points here as well. We could actually fix this by creating a set out of this. And with this, we are sure that we're not sending repeated points, and also we are sure that the points are not repeated here, because we have filtered them, and then we keep only those that are distinct, and then we count them. So now if we run our tests, and you see how clear this is, right? I mean, you are mapping every segment to its points, and you can actually create a helper method for this in segment, for example. Let's go on and create that. We could go to the segment class here, and we could say public stream point, and say
points stream. And we could say we actually need to put this right here. We will put it in our method return point 1 and point 2, and we can replace this with segment point stream. So we have the stream of points, and we check that these points are contained in this list, and then we only keep those that are not the same, so one instance of each, and then we count them. And then we compare the count against the length, and we can actually use this to avoid repetitions. And this is very clear. This is very declarative of what's happening here. We get the points, we check if they are contained in the list of parameters, we discard the ones that are repeated, we count, and then we just check if the counts match. If every point is included, then the counts have to match. If they are not all included, then this one will be lower than this one. Now all the tests pass. So you see how clear everything is here. We have this method here, we have these methods here. It's very simple to read what's going on. You just need to get used to this syntax of sending functions as parameters. This is what functional programming is all about. We haven't even returned any function as an output, but that is something that it can be also very useful. But we haven't found any of this in our requirements, so we don't have to do it. But I think this helps as a great introduction. What do you guys think? Let me know in the comments. Alright guys, this was all for today, and I hope you find this tutorial very useful and this topic about functional programming as fascinating as I do, because it's truly really good. It has improved my programming style quite a bit, and I am really enjoying using these data structures and optional streams. And in our next episodes, we are going to go even deeper into functional programming with scary concepts like monads and monoids, partial application, and some other concepts. But you don't have anything to worry about, because we're going to go slowly through each of them, and we're going to learn a lot together. So I'll be waiting for all of you, and as always, don't forget to smash the like button and leave a comment and share with your friends. I'll be waiting for all of you in the next episode. Bye!